Hi. First of all, I'd like to thank you for inviting me over. It's always nice to leave Rehovot. So when I visited some people here before this talk, and it was very interesting to talk with the and it realized how the science that I'm doing is, because what I'm working on, particle physics, is fundamental science. So there's nothing applied in it. Okay, no one left. That's good. So just to illustrate how fundamental my research is, this is my life in science. So I started working in the high energy physics group with Yoram Rosen and Shlomit Harem, doing Lab 1 analysis, and there were a lot of events in Lab 1. Then after the master degree, I moved into doing a Lab 2 analysis, and there are less events there. In Wisconsin, things got a lot worse. Now, the plot, the y-axis is number of events that are expected to be measured, and it's a log scale, if you haven't noticed. Then I moved to Wisconsin with my family, looking for high-energy neutrinos, and the number of events expected there is 10. We're not there yet. We haven't seen in IceCube any astrophysical neutrino yet. But once we'll start to gather statistics, we hope to have 10 events a year. After 3 years in Wisconsin, I moved to a different type of neutrino detection that I'll tell you about today, using radio waves in an experiment called ARA. And the base case scenario for ARA is to discover 2-3 events a year. When I joined the Weizmann group, I actually came to look for dark matter. And dark matter number of expected events is unknown. It's precise, of course. Now, if you haven't noticed the trend on this plot, that's very reassuring to see my career and then an error going down. So this is that's the game of looking for new physics. It's challenging, it's fun, and it's exciting, and it's a combination of fundamental science, the theory, and also a lot of applied science and engineering, because the projects I'll tell you about are an amazing machine, engineering-wise. So I'll tell you about why we want to do neutrino astronomy. Talk about neutrino detection, why the South Pole. We'll talk about IceCube, the world's largest neutrino telescope, and why it's not big enough. And I'll tell you about ARA, which is my my new baby. And then finally, I'll briefly tell you about some of the challenges in design and construction of detectors at the South Pole, because it's a unique environment. Okay, so the case for neutrino astronomy. So in this beautiful photo, you see the cartoon guy looking at space, at the cosmos. And traditional astronomy, what people have been doing for thousands of years, is using mainly photons. So the photons can be visible light, or photons in radio waves, or X-ray, or gamma, but it's photons. And photons have one big problem, and I usually do it with when I give outreach talks to kids, but I mean, you're engineers, so I'll give it a try. I'm kidding. So if you'll take your hands and cover your eyes, what do you see? You see nothing, right? It's not surprising. That's because it's relatively easy to stop photons. So it's true that it's a little harder to stop X-ray photons, and it's even harder to stop gamma ray gamma photons. But still, it's relatively easy to stop. This is why we look for a different type of a messenger. So what you on this slide, kind of information you can get from different photo measurements. So the cartoon guys took several photos of the crab, and you see the same object in different wavelengths. So you have a radio image, and X-ray image. So it's all of the same object, and of course, astrophysicists can get different type of information from the different wavelength. So we did the hand experiment, right? But it was a little silly. And you all know about satellites and other possibilities to improve our observation ability. But there are a few other things that can interfere with us making astronomical measurement. So this drawing is not to scale. You see Earth, and then far, far away on the left side, you see some sort of astrophysical look at. And if we're lucky, photons can reach directly from this object to us. Very often, space is not empty. There's matter in parts of it. And this matter can stop the photons, like the hand stopped the photons before. But this is also not really exciting. But except the matter that's in space, there's also, oh, I forgot to tell you about protons. Protons are also very likely to be emitted by astrophysical sources. And they can also reach us. They can also be relatively easily stopped by different objects. But notice that the proton curved because it has electrical charge. So if there's magnetic field, it will do some sort of a curvature movement. What else is in there? So except the matter in space, there's also the background radiation you all heard about, which is low energy photons that are flying around. In this case, the background, which is remaining from the, but there are also other type of background radiations. So this radiation can also stop the particles from getting to us. And here there's something really exciting because it's all over the place, this radiation. And the more you look deep into space, then the ray reaching you has to go through larger distances. And it's more likely to make an interaction with the cosmic background. So that's a real problem when you do astronomy with photons or with protons, because you cannot look very, very far into space in some energy scales, because at some point your messenger will be stopped. So why do we need an additional messenger except the photons? So first of all, we want to study opaque or dense sources. Some sources are so dense that the photons, the light cannot escape from them. So it will scatter inside the core of the planet. So there's no way to look inside using photons. A different messenger can give us additional information on the source. So we know what the measurement look like with photons. What will it look like using a different particle? And we can also need a different option for studying the high energy universe. And what you see about in this figure on your right side, it's a little, I'll walk you through it. So this is observable distance in megaparsec units. And the y-axis is log of the particle energy. And here are some scales of the galaxy and the universe, just to give you an oversight of where things at. All the shaded areas, or the line I should say, is where photons start to interact. They have enough energy to interact with the cosmic background. And we no longer see them. And of course, as distances get larger and larger, this shaded area, it's bigger. And so you have this figure, this line for photons. So and you have this curve also for protons. And that means that, for example, above 10 to the 15 electron volt energy, we cannot use photons to observe things that are further than 0.1 megaparsec, because they'll end up interacting with this background radiation. So that's a real problem. We cannot look deep into the high energy universe using photons or protons. So as you can guess, in IceCube and ARA, we are using neutrinos to look into space. So just a brief reminder, a neutrino is an elementary particle. It's part of the standard model of particle physics. It was invented in 1930 by Pauli, trying to explain some problem with energy conservation in beta decays. It took almost 30 years until it was finally discovered and measured in the lab. The neutrino has no electrical charge. It comes in 3 different flavors. There are 3 different types of neutrinos. But for this talk, it doesn't matter. I will not get into it. It has very, 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 very small mass. In fact, until a few years, we thought that it was completely massless. But it has a small mass. It's part of the standard model of particle physics, and it only interacts via the weak interaction. And I'll show you how weak or how rare the weak interaction is in a few minutes. And since it was on the news for a while, a few months ago, so no neutrino does not travel faster than the speed of light. So neutrinos are not a rare particle. Again, if you'll use the same hand you use to cover your eyes, like this, then trillions of neutrinos will go through your hand every second. And there are many, many natural neutrino sources. The line is energy scale. Just to give you some references, where it's in the applied world. So you see visible light is around 3-4 eV, TV screen around 20 keV. Then we have LAP, the particle accelerator at CERN, 45 GeV, and the LHC with the 70 eV. So the most energetic, we are able to accelerate particles up to 70 eV. And it's and it takes a lot of electricity to get there. So that's what we can accelerate particles to. Let's see what neutrinos are like. So first of all, we have the solar neutrinos. They were detected in 1968. They taught us a lot about neutrinos and particle physics, but they have low energy. So I won't talk about them anymore. At slightly higher energies, we have neutrinos from supernova explosions. So we were able, not IceCube, but other experiments measured one supernova in 1987. And it was a great discovery. It gave a huge boost to astroparticle physics. But supernova neutrinos also have low energy for IceCube. So I will not talk about them anymore. Then there are the atmospheric neutrinos. These are neutrinos that are created by, in the atmosphere by interaction of cosmic rays. And they come to us all the time from all over, and they can get to pretty high energy levels. IceCube can detect these neutrinos, but what IceCube is really looking for are all the astrophysical neutrinos that you can see on the left side. And these are neutrinos that can get to us from GRB or AGN. I'll tell you a little more about the GZK neutrinos in the next slides. And so that's the scientific menu of IceCube, and you can see with the blue shade the energy ranges that IceCube is looking at. The other experiment we'll talk about, it's called ARA, is sensitive to much higher energies. So what we're trying to do is to add another photo to this gallery and have a photo of the Crab Nebula using neutrinos. And this will give us a lot of additional information for different models. So one example of the science case. I know probably 80% of you came here to see photos of penguins. We'll get to that, but just a little science. So please hang on. So there's a very disturbing mystery concerning the cosmic ray. So cosmic ray, it hit us from all over from all directions. A lot of research has been put into the lower energy cosmic rays, which are roughly from here to the left, and there are a few very strong models as to what accelerate the particles to such a high energy. But we know very, very little about the source and the origin of the very high cosmic rays at this end. So this is an energy scale at log. So these are huge, huge energies. And you need huge accelerators together. And the source and the composition and what the acceleration mechanism is like for these very high rays is not known. So we hope to use neutrinos to solve this problem because we cannot use photons. They cannot reach us so far away in such high energies. And a lot of models are expecting neutrinos to be created in the acceleration source. For example, like GRB. It was a little on the news a few months ago about the IceCube results, the GRB models. I don't have time in this talk to get into more details, but if you want to talk about it offline later, let me know. It's an exciting result. So one of the missions IceCube has is to look for a point source of neutrinos and hopefully learn about GRBs. So correlating the point source with a GRB explosion and telling more things about what's going on in there, because we have an additional degree of freedom. However, there's an additional cosmic connection. It's not just the point source. And I'll take you back to this cartoon that I showed you before about the particles being stopped by the cosmic microwave background. Let's get rid of all the things that are not relevant. Okay. So you saw the proton hitting the cosmic, the photon, the cosmic microwave background photon. But what's going on from here? So let's look into more details. So we have a photon-photon interaction, and we get at the end 3 neutrinos and the neutron that decays to a proton. And the proton has less energy than the original proton. And then this proton continues to travel, and it will hit another photon eventually. And it will create another 3 neutrinos, and it will lose a little more energy. Now, just a remark, there's an additional neutrino that's emitted by the neutron decay, but it has lower energy, so we don't care about it. Okay, so, and then we have more neutrinos, and this process will go on and on and on until the proton will lose enough energy, and it will be under the threshold for this interaction. And when it's under the threshold, it will just go through whatever distance and reach us. So this is called the GZK effect, after 3 great scientists that I won't try to say their names. And it means that propagating cosmic rays, they interact on the photon background and lose energy. It means 2 things. First of all, we have the GZK cutoff. It means that no cosmic rays from protons above 10 to the 20 eV can reach us, because they interact with the background and slowly lose energy. But it also means another thing, because we have a lot of neutrinos. So we have less cosmic rays, less protons, but more neutrinos. And we all love neutrinos. And if you will, so that's the second cosmic connection. And these neutrinos are considered to be a guaranteed source, because we know there's high energy cosmic rays, and this interaction is so basic, it has to be there. If you look on the cosmic ray spectrum real closely, so the GZK cutoff is at 19.5, 10 to 19.5 GeV. And I think that, do you see here that there's a bump in the, do you see that there's something there? So that something is definitely going on there. Let's zoom a little more. So that's just the high energy part of the figure you saw before. And indeed, when you zoom in, you see that right where we expect it to happen, there's a huge decrease at the flux. So indeed, we see something that looks like the GZK cutoff when you look into cosmic rays. What we do not know, however, is whether it's really the GZK effect, or maybe the source, the acceleration source, is running out of steam. Maybe it's just there's a limit to how energetic the cosmic rays can be. So for that, we need neutrinos to study the cosmic rays and learn more about their source. So, how do you detect a neutrino? Neutrino interact only through the weak interaction, and that's a question for you. To stop a solar neutrino, we need 1,000 kilometers of lead. So to stop a photon, a visible light photon, how much do we need? 1 centimeter of hand. So to stop solar neutrino, we need 1,000 kilometers of lead, and lead, of course, is very dense material. So who thinks that's about right? Raise your hand. Who thinks we need more? Who thinks we need less? So all the rest do not think, or? Okay, so the answer is, you can probably guess that it's more. It's amazing to see by how much more it is. So to make sure we stop 99.9% of the solar neutrinos, we need 10 light years of lead. That's 1 million times the distance to the sun full with heavy, dense material. So that's a very large hand to stop. Now, it's great because it means we can, neutrino can get to us from very far, far away parts of the universe, because they just go through everything. But unfortunately, it also makes them very hard to detect. And that's my only formula for today. And it tells you how big should our detector be. So the number of neutrinos that we detect depends on the flux, how many gets to us. So the solar neutrino flux is about 10 to the 7. I don't care about the unit at this point. But we're not interested in solar neutrinos. We're interested in higher energy neutrinos that are more rare. And they have 10 to the minus 8-ish flux. So we lose 15 orders of magnitude here. Cross-section of Thomson scattering, which is an experiment most of you probably did in undergrad school, part of a physical lab, is 10 to the minus 24. Again, the units do not matter. For the neutrinos, is 10 to the minus 34. So we lose another 10 orders of magnitude. Density of nucleons we cannot do much about. So the only thing we can gain with is the volume. And if we'll put all the numbers in, you'll see that to detect a few high energy neutrinos, we need a kilometer scale detector. Detection principle is pretty elegant. We have an astrophysical neutrino reaching our detector. If we're lucky and it interacted in the ice, it will create a different charged particle. In this cartoon, it's a muon, which is the fat brother of the electron. And this muon moves faster than the speed of light in matter, not the absolute speed of light, of course. And when particles are moving through, charged particles moving through a medium higher than the speed of light. In this matter, they emit the Cherenkov radiation, which you can see here as 2 arrows. And what we do, we look for this signature by using an array of detectors. So to build a neutrino telescope, what we need is a lot. We need a lot to make a measurement. We need it to be cheap, because someone has to pay the bill eventually. It has to be transparent, because the whatever radiation we're looking at has to propagate. And it has to be dark, so we will not have any background. So we look for a lot of cheap, transparent, dark stuff. One option is ice. Any guess what the other option is? Water, right. So the other option is water. And there are several experiments running in lakes or in seawater. And there are a lot of pros and cons for ice versus water. I will not go through it once here. I do like to mention one very critical difference, and that's the following. So these are the photos we send home. And these are the photos they send home. So this, it can be very frustrating. I mentioned the supernova 1987A. I'll give this as an example from of a smaller neutrino detector. That's Super Kamiokande. And what you see here is a huge tank filled with water, halfway filled with water. And all the small points around the walls are photomultiplier tubes. If we zoom in, we'll see that inside the boat there are 3 people who are just sailing in the tank and cleaning and making sure everything is fine with the PMDs. This tank is completely full with water eventually. The people are out of it. And they're looking for light that is created by a charged particle that's created by a neutrino. So this is a very successful experiment called Super Kamiokande, but it's sensitive to lower energies. So we're looking for something bigger. And for that, we're going to the South Pole, to Antarctica. That's an aerial view of the South Pole. I'll give you some references. That's the way home. That's the ski runway where airplanes land. They land, of course, on skis, not on wheel. That's the South Pole Station on the left, where you live, you eat, you work on the computer, you sleep, not a lot. And the South Pole marker, the actual geographic South Pole, is more or less where the arrow is, and it looks like this. Now, if we'll zoom in, that's the z-axis of Earth. So whenever you drew the Earth and z, so that was it. That's the road to work. So all the scientific activity is done in this of the ski runway. It has a very dramatic name. It's called the dark sector. It's called dark because we try to minimize the amount of background in it. So that's where we have our detectors installed. And IceCube is buried a square kilometer, more or less, around the here's IceCube. So that's the surface. Here's the South Pole Station. And what we do is to drill 2.5 kilometers into the ice. We deploy strings with light detectors, covering area of a square kilometer. And we look for a particle that will emit light. So just because I like to make fun of my past, when I worked on the particle detectors, that's Atlas, where they just discovered the Higgs, which is also a great discovery. So we always used small people to show how big the experiment is. And every year the people got smaller and smaller, the detectors got bigger and bigger. So guess what I'm going to use to show you how big IceCube is? That's so satisfying. So IceCube is a cubic kilometer detector. $280 million project. Construction ended a few years ago in December 2000. 2.5 kilometers deep in the Antarctic ice. We have 17 meters vertical spacing between the various strings. I'm sorry, between detectors, meters between strings. And it's optimized for very specific energy range. For example, to look for the GRB. IceCube triggers quite often. Even though the neutrinos we look for are rare, it will trigger at 2 kilohertz on atmospheric muons, which is our background radiation. It will trigger about 10 times a day on neutrinos created in the atmosphere. Now, this is not our science goal. People are doing science with it, but it's not the main objective. What we're looking for is for cosmic neutrinos and cosmogenic neutrinos, which we expect to have a few a year. So we have a very high trigger. We need to look for very model that does all the 10-inch PMT in a glass sphere. Very low power consumption, only 3 watts. And time resolution of 3 nanoseconds. About basketball size. And we have more than 5,000 of these buried in the ice. Now, in the poster, they hang with my photo. You see me holding one of them near the South Pole marker. So, yeah. That's a real IceCube event. Each dot here is a photomultiplier detector, and the colored circles are light hitting the detector. So the larger the light is, the more the larger the circle is, the more light was detected. Red and blue means time. Red is early, blue is late, and you can actually see the particle. You see something going up through the detector. Of course, the red line was added later. We have reconstruction algorithms.
What wavelength is it?
With the IceCube visible to UV. And it's also interesting to see timestamps. So this is running in nanoseconds. And it was not an easy task to have this huge array, all detectors, all small detectors, being correlated in time to within nanoseconds. With ARA, we'll have to do even best. So using this, we can tell when the event happened, where it came from, and how energetic it was. We have a great filter, Earth. I told you about the muon, the 2 kilohertz background. These muons cannot go through Earth like neutrinos can. So what we do is a very tricky thing. Instead of looking up into the sky, we look down into the sky. IceCube is at the southern hemisphere, but it's not looking at the southern sky, it's looking down. Because the only particle, as far as we know, that can reach us from the other side of Earth is a neutrino. And this stops all of the black arrows from confusing us. And we have a lot of atmospheric neutrinos, and we need a different technique to separate the atmospheric neutrinos from the astrophysical neutrinos. Here's a photo.
How can you stop them if you said that nothing can stop them?
The atmospheric neutrinos, we do not stop them. We use analysis techniques to separate them. Here's a photo of the last season of construction of IceCube. That's the ICL, the IceCube lab. And all the cables, all 80 strings, they go under the ice through this hole here, up into this tower and into the computer lab. That's inside the building where computers process the information and send it to the north. We had a huge problem of the computers overheating. That's true, it's not a joke. How do you drill so deep? So we use hot water, just a big pipe of hot water. We do need a 5 megawatt engine or heaters to warm enough water to make one hole. It takes several hours. Here you can see the hose that's used to drill the hole. It's slowly going down into the drilling tower. So under this thing, there's a hole about this this wide that goes 2.5 kilometers down into the ice. And here you can see a photo of the power plant used to create power to heat the water. Some photos of drilling and string installation. Here's the drill, it's just a pipe. Here's the detectors waiting to be deployed, and one of them being connected. And it will go down into a long journey. Some freezing facts about the South Pole. So it's about 13 hours flight from New Zealand. Tiny room. The bathroom is in the same building. It's not a joke. Satellite coverage. There's communication half a day. 2 minutes. You get altitude sickness. There's low oxygen. There's light all day and night during the summer. The air is very, very dry. Temperature during the austral summer around minus 40 degrees. It's very windy. Winds are usually from the north. In this joke, that laughter always comes in like 2 waves. That's it's only reachable during the austral summer, and we do have winter overs that babysit the experiment and station. So these are people that are stuck in there for 13, 14 months, but it's just for one night. So it's. So why is this great IceCube not enough? Here's a photo of the neutrino sources, the neutrino sky. On X you have the energy, and on Y you have the flux, how many neutrinos are reaching us. So the low energy neutrinos, we have quite a few, and we need detectors about 100 square meter size, like Super Kamiokande. To get into the GRB and AGN range neutrinos, we need a 1 square kilometer detector like IceCube. But if you'll do the math, you'll see that for the cosmogenic neutrinos, these are the GZK neutrinos we talked about before, you need a 100 square kilometer detector. That's a large area to cover. So why not build a larger IceCube? I mean, it's working great. We know how to do it. The reason is money. Any additional IceCube string will cost about $1 million. And let's say we want to make IceCube 100 times larger. That's another $100 million. That's a lot of money. Even if you do some optimization of the geometry, it's still a lot of money. So what we need is a better technique to detect neutrinos. And the solution is to use Cherenkov, the same Cherenkov photons, but not in visible light wavelength, but in radio frequency. And the reason is that radio has longer attenuation length in the ice. It means that you can put your detectors further apart, and less hardware, then it costs you less. There's also less scattering of radio frequency in the ice, so it's easier to reconstruct the events. You don't need to drill wide holes. A PMT needs a large surface area, and an antenna is an antenna. Antennas are more robust than PMTs. You detect 200 meters. South Pole is very RF quiet, no EMI, electromagnetic interference, and we have a huge volume of ice. Easy to detect RF. So there are many great reasons why you want to do it in RF. There's only one problem. If you look at the Cherenkov formulas, you'll see that there are less photons emitted in longer wavelength. So it's a great idea, but it's not going to work juice in the long wavelength. And the solution came Mr. Askaryan on the Askaryan effect. He said that the very for high energy radiation becomes coherent and it is deductible. I do not have time to go into the details of the effect. I'll just tell you that the idea is that instead you have a shower of a lot of particles. And instead of having each single particle doing its own Cherenkov wavelength, longer than the size of the shower, this Cherenkov radiation, all the Cherenkov radiation become coherent. And instead of seeing 1,000 electrons each emitting its own Cherenkov, you see one huge charge emitting one cone. And this has become detectable. There's a lot of simulation work done on the Askaryan signal. It was measured in a lab, so it's not science fiction. And there are a few options where we can put such a detector. Air is not an option because it's too thin. Water is RF lossy, so you cannot detect RF in water. The lunar regolith, surprisingly, the moon, the sand on the moon, is RF transparent, and we have there are telescopes watching the moon looking for Askaryan signal. Ice has very good attenuation length, about 1,000 meters, and there are a lot of activity that was done in previous years to look for Askaryan signal in the ice. And also salt is RF transparent. And there's one activity trying to build such a detector in salt. So a new collaboration was born, just what the world needed, another collaboration. We have more than 10 institutions, US, Europe, Taiwan, Japan, now also Israel. Strong interest from many other groups. It's a growing collaboration. We have 2 units deployed in shallow depth, and we plan to have another 3 units deployed this season. In fact, I'm supposed to be there in a month and a half. So what we are trying to do is we're looking for a fast radio pulse in the ice using an array of antennas. We try to reconstruct the vertex or where this signal came from using time differences between hits. But we're only interested in events that happened under the ice, because above the ice there's relatively a lot of RF noise, and the ice is quiet. And then we try to reconstruct the Askaryan pulse using various information from the antennas. We need to know a lot of things to do correctly. We need to know the attenuation length of the ice, which depends on frequency and depth. We need to know the index of refraction, which depends on depth, the detector response, and the characteristic of the Askaryan signal. Each bullet here, it's quite a lot of work. To understand the detector, we did quite a few calibration. We're still doing them, and this is just, I'll flash this slide quickly. You see an antenna in an anechoic chamber, and on the left you see the antenna gain based on this measurement, which is what we expect. The concept of ARA is to have 80 square kilometer, 37 stations. That share power and 80. Each station, each white has 4 closely spaced on the surface. Each string has 2 vertical and 2 horizontally polarized antennas. and a pulsar, a calibration source that's used to test our systems. We are sensitive to 800 megahertz. Different antennas, different filters. It's it. And the cable passed through the antenna. So the antenna, if you'll imagine a string and an antenna, the antenna is designed in a way that the cable can pass through it. And this is to avoid the shadowing effect. So this is optimized for discovering GZK neutrinos. And here's a neutrino that made the Cherenkov cone. You can see the RF radiation propagating to this channel. And we use the information here to make the event reconstruction. That's a time resolution figure. I'll continue. OK, so now it's another game. It's called Guess the Experiment. So one is IceCube, one is ARA. Can you tell which one's which? That's easy, right? IceCube are the antennas. And here you can see two types of ARA antennas. Hole diameter. Which one's ARA, which one's IceCube? Also easy, right? ARA has smaller holes. That's why it's so great. We don't need huge holes. It costs us less money. So that's IceCube and that's ARA. Drill camp. So for IceCube, we had a huge drill camp. We needed 30 drillers on ice to operate the drill each season. It's 31 if you include the supervisor. With ARA, we need to get from point to point very quickly. We need to cover a large area. So we cannot have this huge camp. What we have is a drill on wheel. So here you see the ARA drill on a sled. And in fact, it was very useful in a Christmas party. They turn it into a steam. It was very dramatic. So you see the money that's been put into fundamental science has a good use. And finally, guess the experiment based on the author list. So of course, ARA is a younger, smaller collaboration. We have less authors. So I have a few slides building such. And if I've with two here, I know I have 2 more meetings after this talk, and it's really exciting and interesting for me to see what's going on in the real world. Because us physicists, we think we can do everything, and that's including building a digitization board and programming the FPGA and planning the communication scheme. But apparently, yeah. I mean, it will be nice to hear new ideas, and I'm interested to talk with anyone who's interested to hear. So, what are the pros of building a detector at the South Pole? So we have well-established infrastructure from the South Pole Station. We have a lot of dark, cheap, transparent stuff. Ice is the polar ice has very low radioactivity. We have low EMI levels, no background. The temperature is stable after deployment, and we have many photo ops. That's just. What are the cons? It's very expensive. We need to ship everything through airplanes, and for example, to drill one IceCube hole, we needed 7,000 gallons of fuel. That's a lot of fuels to send over. Deployment season is short, November to February. That's the Austral summer. There's limited or no hardware maintenance after deployment. In IceCube case, the detectors are frozen in the hull. You cannot take them out to repair. Weather conditions can be tricky. There are delays with arrival and departure of resources. It's cold, even during the summer, and you get altitude sickness. There's no hardware store nearby, so you need to plan ahead. It's terrible to be there and discover that you accidentally brought the metric wrench. And it's a pretty long commute. Some of our design requirements: the detectors need to operate 10 years after installation without problems. And with IceCube, we have 99 point, I don't remember, it's 99 point something success rate. So the failure rates of the detector is very low. The detector is not accessible, and you need it to be operated remotely. And also take into account that the communication might not be stable. It needs to be resistant to RF interference, because we have RF experiments that work there from time to time. We need to have in situ calibration and diagnostics to see what's going on. We want to have efficient triggering, because we have background rates, high background rates. And we have limited communication bandwidth, so we want the filtering to be efficient enough, so we will only transfer the interesting stuff. It must be low power, because fuel is expensive. And everything must fit into a Hercules airplane. So this is the only way to get there. And the high stress during freeze back, that's for IceCube, as the water froze back into the unit 2.5 kilometers hull. So it's colder on the surface. So we had ice on top, and then you have this huge column of water, and you know what happens when you put water in the fridge and close the bottle. It's explode. So we saw the same effect, and the photo detectors had a lot of stress, a lot of pressure. So this had to be taken into account. The scientific requirements: low background to optimize sensitivity. That's concerning the threshold tuning. We must have polarization information. That's the only way to identify the Askaryan pulse. And the excellent time resolution. Picoseconds is what we're after. Flat frequency response, so reconstruction will be easy. And a strong enough calibration source in the ice that we can see tens of kilometers apart. Some of the design challenges. It's easy to make a vertical antenna to fit into a thin hull. It's much more hard to make a horizontal, the other polarization antenna, to fit into a hull. It's even more complicated when you try to avoid cable shadowing. So these are not simple antennas. We need fast and efficient drilling, communication and power over large areas. Okay, I don't have time to talk about the calibration source at all. And these are, I'll just flash this because I'm way out of time. These are some of the decisions we need to make in the design of experiment. The hull diameter, should the hull be wet or dry, with water or without water? How deep should we go? What frequency range do we want to detect? And what filters do we want to use? What should be the waveform sampling length, and so forth. So this is where we're at the stage where we are designing a new experiment. And just to show you, just to summarize it all, this is a sensitivity plot. And the lines you see are for different experiments. It tells you how strong should the source be, so a detector can detect it. So this is what the detectors can detect. And the lower the line is, the more sensitive the detectors are. And you see the red ARA line. And that's the GZK, expected GZK spectrum. So when ARA will be finished, we should be able to see the GZK sources quite easily. So that's the summary. I'll let you browse through it. And if you have any questions, yeah.
When you talk about polarization, relative to what?
Yeah, I know. That's why I did a vertical, and it's just two polarizations. It's
where, if the hole is vertical in the sense of into the ground, where are you trying to look through the earth in that direction? Because then an antenna that you stick in as a pole, actually this is a 0 p
we're not looking straight down. We have this huge volume of ice around us. And also, let's suppose that the neutrino did decide to interact right under my antenna. Each station has several antennas, yeah. So we can...
It would be interesting to see what maximum sign that you can extract in your lifetime from this. What do you expect to extract? Because it's a very huge endeavor. What is the sign that can be extracted?
With ARA?
Yes.
Okay. So with ARA, we hope to make a constraint on the GZK neutrinos, which we can use to study cosmic rays. And it's, I mean, I don't have time to get into the details, but it's a big thing. Discovering or not discovering GZK neutrino is very important. And then the flux and the flavor of the neutrinos, if it's a electron muon or tau neutrino, and the it all gets into the models. And there
different neutrinos in this scheme?
in these energies there aren't a lot of neutrinos. It's just
no, what is it? How do you separate between the three different types of neutrinos?
the flavors.
Yeah,
It's with IceCube it's relatively easy. With the ARA, it's also possible. It's harder. It's based on the model the shower is developed. So different types of showers will have different models. It's not easy, but it can be done. With IceCube, it's easy to distinguish electron neutrino and muon neutrino. With ARA, it will be more complicated. Yeah. Yeah.
Who paid for this experiment?
It's mostly the NSF, the National Science Foundation, with some small European support. But it's an American project.
Yeah. So how smart is it to put a lot of detectors to IceCube? They all fight for the same neutrinos.
I'm sorry, how?
Is the ARA and IceCube competing for the same neutrinos or not?
First of all, there's no competition. We're all friends. Second, they have different energy sensitivities. ARA will not be able to discover the neutrinos IceCube C. It's just below the noise level. And the IceCube is too small to be really sensitive to the neutrinos ARA will see. In some cases, they can support each other, but we're not planning on that.
Okay, maybe we'll take a couple of more questions, and then she's here for the rest of the day, and then you can meet her. So let's take a couple of one question in the back over there. Someone did a question? Yes.
If you will detect a neutrino of the disk, will you be able to know something about it, where it came from? Or
When are we going to detect it? Now or in 10 years? Because now no, we will be able maybe to estimate maybe its energy, but in 10 years we will have more stations and we can reconstruct the direction of the neutrinos. It's not a simple problem because we need to reconstruct the Cherenkov cone, but in 10 years we should be able doing it.
Okay, let's thank the speaker.
Hello,